This is sort of a really brief introduction to carboxylic acids. We're not going to cover the organic reactions of carboxylic acids because you'll do that as you learn about acyl chlorides, amides, esters, those sorts of things. What we are going to look at is the functional group, the rules when it comes to naming the ones that you will meet this year. The rules change a bit as you get more complex chemicals, okay? But for the ones that you meet this year, I want to show you how we'd name them. We're going to look at why they've got particularly high boiling points. It's probably the most important physical property. And we're going to look at their acidic properties. In other words, why they act like an acid, why they're called carboxylic acids. All right? So they are the basics. It is stuff that you should have a feeling about most of this already from the stuff you did last year in Level 2 chemistry. So the first one is you'll often see the functional group drawn like this with an R. And an R can actually be a hydrogen atom, by the way, in this particular compound, because there is such a thing as methanoic acid or formic acid, where that is an H. But usually we're looking at any carbon chains. So when we're looking at an organic compound, we're looking for the COOH. Of course, if it was just an H, it would be an aldehyde. Okay, and if this was a carbon chain, not an OH, it would be a ketone. So, and if this was O and then a carbon chain, it's a thing called an ester. So we're looking for this exact thing, COOH. And the reason you'll see it written COOH, for example, like that, rather than CO2H, is this is kind of showing the structuring. The carbon is bound to both oxygens, not the two oxygens are bound together. So that's why we often write them that way rather than CO2H. All right? So that's what we're looking for, COOH, or it drawn something like that. For naming them, for the ones you're going to meet this year, you can very safely assume that it's on the number 1 carbon. And then find your largest carbon chain from there. So 1, 2, 3, 4. Alright, then you can look for any side chains and that sort of thing and number them appropriately. So I tend to name it backwards. I say it's 4, so it's butanoic acid. But then I've got this little side chain of 1 carbon. So now it's methyl butanoic acid. So an isomer of pentanoic acid, in other words. And then I'm using my numbering where this is the number 1. So it becomes 3. Methyl butanoic acid. So for all carboxylic acids you will meet this year, you can say that that's the number 1 carbon when you're naming it. It'll make it easier to name. Okay, so it's even true for amino acids. Technically the amino group should be higher but that in the classification, but that's okay. For this year, it makes life much, much easier if we call this the number 1. Okay, so name it with the carboxylic acid group once identified as being your number 1 carbon. Okay. Anything that is more complex than something like that, you would be given the name for, because it'll have probably a name that's come from biology and from biochemistry rather than from pure chemistry. The other side chains you need to sort of be aware of that you can see, sometimes you'll see these have got OHs coming off them. So if it's got an OH as a side chain, it's no longer called an alcohol in this case because this is the functional group that gives it the majority of its properties. So you'd call that a hydroxy something. And of course then you've got your other side chains, NH2 would be amino. And then your main other ones are going to be things like your halogens, so halides, so chloro such and such, bromo such and such, that sort of thing. Okay, so there are the 2 other ones to note. That's how you'd name them if they're in a carboxylic acid. Alright, so if that was not a CH3 but was an OH instead, you'd call it 3-hydroxy butanoic acid. If it was an amino group, 3-amino butanoic acid. So we don't have to number where the butanoic acid part or the acid part is, it's on number 1. Okay? One of the key physical properties we find about carboxylic acids is they're very, very high boiling points. They are remarkably higher than we would expect for their size and the polarity of the functional group. They are considerably high. You wouldn't actually expect this to have a much higher boiling point than ethanol, because this O here doesn't contribute towards, or shouldn't contribute towards hydrogen bonding at all. Okay? Should only be the OH, just like in ethanol. However, what happens is the smaller, not the big ones, but the smaller carboxylic acids travel around as dimers. Mer means unit, like polymer is a many unit compound. So plastics and nylon and things like that. So a dimer is made up of 2 units. And what happens is hydrogen bonds form because of the actual shape of it, geometrical shape. These H's and O's line up beautifully to create a dimer. This creates a much larger electron cloud than just one of them on its own, and that allows it, that results in it having a much higher boiling point than we'd expect. Okay, so because the smaller ones, formic acid or methanoic acid, ethanoic acid, propanoic acids can travel as dimers, they have much higher boiling points than we would expect. Okay, just a thing worth noting. This is what makes it really easy to use things like reflux to get high yields of these. It's also what makes it very useful to be able to extract the aldehyde if you're oxidizing by distillation, because their boiling points are so high that they're not going to have a chance to be made. The aldehyde will be removed before the reaction can occur. The last thing I want to go through is the acidic properties, which is always one that people assume, oh yeah, we know this because we know about hydrochloric acid and all that sort of thing. But I just want to check that we do actually have on record what they are. If you were to do a chemical test with litmus paper or a universal indicator or anything like that and use that colour change to confirm that an unknown is indeed a carboxylic acid, you're still expected to show an equation for that. Even though it's a simple test, there's actually a chemical reaction occurring, so you're meant to show something happening. So a piece of litmus paper, dry litmus paper, hovering over the top of some, let's say ethanoic acid, because it's a nice easy one to use, ethanoic acid won't change colour. Damp litmus paper, though, will go red. And the reason for that is the dampness is important. It is actually the reaction between the carboxylic acid and water that gives it the acidic properties. Okay? Now, we'll never experience that firsthand because we're made up of so much water that the second we touch a concentrated acid, it reacts with the water in our skin and on our skin and starts hurting us if it's at that concentration, 100%. So we will never experience that firsthand. We will always go, oh, it's acidic. It started corroding the whatever. It turned the litmus red, and that's because of its reaction with moisture. So you need to be able to show that. So I'm going to use ethanoic acid as my example. CH3COOH. The moisture is the giveaway. It's going to be water. And it's an equilibrium reaction because these are weak acids. They don't fully dissociate. Roughly 1 molecule in 1,000 will dissociate. Roughly. Okay, it's about 1 in 1,000 will dissociate. The rest of them stay together as the molecule in the dimers, actually. All right? Either in the dimers or with water molecules in between, but not dissociated. Just still CH3COOH. But 1 in 1,000 will dissociate. Roughly 1 in 1,000. But acids, we need to remember our Bronsted-Lowry definition of acids. Acids are proton or H plus donors. They will give away H plus. So what they're going to do is become CH3COO minus, and they're going to increase the concentration of hydronium ions in the solution or on the damp litmus paper or whatever. That increase in hydronium is what causes the colour change in our indicator. So it's the increase in hydronium ion concentration, even if it is only 1 in 1,000, that's a lot. That's a pH change of about 3, if it's going to get lower by 3. So we also need to be able to name these things. If this is ethanoic acid, then this is the ethanoate ion. Okay, if it was Propanoic acid, it would be the propanoate ion. If it was butanoic acid, the butanoate ion, and so on. Alright, I'll write them so you can see the pattern there. So this becomes important when we look at the other acid reactions. Acid-base, acid and metal. So if I took ethanoic acid and I reacted it with magnesium, what would I make? What happens if I put hydrochloric acid with magnesium? Hydrogen gas, someone's just whispered. It gets hot because it's an exothermic reaction. It fizzes, great. So we're going to make hydrogen gas, and we know that. We've done this test a million times. What's the difference then between ethanoic acid and magnesium? What's going to be different? It's a weak acid. What does it mean?
It means that the rate of reaction will be slow.
Great.
It's a lower concentration.
Good, because it's the hydronium ions that are actually reacting, not the acid particles themselves over here. So because of the lower concentration of hydronium ions than in the same concentration of hydrochloric acid, the reaction rate is lower. But the products are the same. You still get the same volume of hydrogen gas eventually, if you're using the same volume and concentration of acid. So everything else is the same, it's just rate of reaction. It's just rate of reaction because the concentration of hydronium is lower. Okay? Eventually all of this will react. Eventually all of it will react. So if eventually all of it will react, it's not an equilibrium reaction. Okay? And this is where it gets really confusing because we don't show it as the hydronium reacting, we show the acid reacting. That's just our convention. Stick with ethanoic again. I'm going to use magnesium on purpose because it makes a 2+ ion, whereas it's quite obvious there that my ethanoate ion is a 1- ion. They don't cancel out. So I'm going to need to balance this. Because this eventually will all be used up if I had enough magnesium, I use an arrow. I don't use an equilibrium. It can't go back into magnesium metal. The magnesium metal will be destroyed, as it were, be turned into an ion. So, hydrogen gas, someone said before, brilliant. So let's put that over here, H2. That's kind of the giveaway that I need 2 of these, because the ethanoate ion has only lost 1 hydrogen. So I need 2 of them to make my 2 hydrogens there. Alright, which is also going to give my giveaway, be my giveaway for what the formula for magnesium ethanoate is. There's 2 ways to write it. You can write it as CH3COO minus, and there'll be 2 of them of course, so 2 in front of it, plus Mg2+, because they'll be in solution. These ions are quite soluble. Or you can write it this way. And both of them are correct. I like that way because I find it tidier. It's just a personal preference. Again, going to give you the names for these things, or the product. Okay.
Can you write the other way as well, just so we can see?
Yeah, I'll put it in a different colour though. Okay, so that's the other way I could write it. As separate ions and then the H2. I need to balance it though because of the H2. I have no choice on that. The H2 means I need 2 of these, which means I need 2 of them. Okay. So we can follow that same pattern for any of the reactions that I would expect to see with any acid and any other substance. So acid and base would make a salt plus water. An carboxylic acid plus a carbonate would make a salt plus water plus carbon dioxide. So they're all exactly the same. What is different about it is that you have got a slower rate of reaction. That's all. So carboxylic acid is just a very good example of a weak acid. Okay. Any other questions before we stop there? Okay, so this is your overview, as it were, of carboxylic acids as acids, talking about how to name them, to explain why their boiling points are a bit higher than we'd expect, because they are very high and that's very useful for making them and for making the precursor for them, aldehydes. And then you have to be able to show the acidic properties. If you're using it as a test for something, you've got to show it dissociating to increase the hydronium ion concentration. If you're showing it compared to a strong acid, you need to show the chemical reactions for those and just explain that there's a difference of reaction rate, and that's all.